My name is Bill Kinney, and this is part 7 of Multivariable Calculus with Mathematica. It's also part 7 of a subseries about calculations with parametric curves. In this video, we will be finding the slope of a cubic curve in two ways. One, using a method from what's typically taught in Calculus 1 called Implicit Differentiation, and a second way using a parametrization of the same curve. And we'll see that we get the same answer. So here's our example. We want to find the slope of a curve, meaning really the slope of its tangent line. This is the curve. It's a cubic curve because it's got an x cubed involved. This is actually the exact same curve that we looked at with video number 6. We're focusing on a specific point. We want to find the slope of that curve at that point in two ways. One, by using implicit differentiation. Two, by using this parametrization that I'm telling you. This is the parametrization that we guessed would work in the last video, and we did confirm it works. And here in blue I'm noting how you can confirm that it works. This is a review of what I showed in the last video. Essentially, you need to plug in the x and y coordinates as functions of time into both the left and right hand sides of the original equation, simplify in terms of t, and see that you get the exact same thing at the end. In this case, t to the 6th minus 2t to the 4th plus t squared in both cases. Also, the entire curve is traced out as t varies from negative infinity to plus infinity. Alright, but we're focused on finding the slope. Here is the curve. I've made an animation right away to start here this video to show what's going on. In this black dot here, that's the point of interest. Again, the point 1 comma negative square root of 2. We should technically verify that that point is indeed on the curve. If you plug it into the right hand side, you've got to take 1 cubed plus 1 squared, which is 2. And if you plug y into the left hand side, negative square root of 2 squared is also 2. The left and right hand sides are equal. This point is indeed on the curve. And I plotted it down here with list plot. There's the point right there. You can look at this code if you like, pause it, and if you've got Mathematica, you can try typing it all in and seeing if you can reproduce it, and better, you should make sure you try to understand it. Here's the actual animation. You see the curve coming up, the parametric curve. First of all, the blue curve itself is created with contour plot. That is the cubic curve, the entire curve as an implicitly defined curve. The red curve that you see being traced out, that is the parametric curve, which is tracing out the given cubic curve based on the parameterization that I showed you. We want to find the slope of the curve at this black dot right there. That's our goal. How do you do that? First of all, with implicit differentiation. What you do is you start off with the equation for the curve. Y squared equals x cubed plus x squared in this case. And you look at this equation and you say, I can think of y as a function of x. Now, it's not always so obvious that you can think of the equation as defining y as a function of x near a given point, in this case the point in question, 1 comma negative square root of 2. Here it's pretty obvious because you could clearly take plus or minus square root of x cubed plus x squared, and in fact you would take the minus square root because the second coordinate here is negative. So it's pretty clear that you could solve for y as a function of x, but in general it's not always clear, and you always make the assumption that the given equation does define y as a function of x near the point in question. Based on that, you then differentiate both sides of this equation with respect to x. Now the right side is easy. That's 3x squared plus 2x. What about the left side? Does that differentiate to 0? No, it doesn't, and that's the key. Because we're assuming y is a function of x, you need to imagine the y is replaced by some function of x. You might call it h of x or something. And it's like you're differentiating then h of x quantity squared. It's not traditional to actually put an h of x in there, though you could. But you need to imagine it. And because of that, you really need to use the chain rule. You bring the 2 down in front, and you multiply times the y, which is the h of x. And then you, by the chain rule, multiply times the derivative of the inside function, the h of x, in this case the y, with respect to x. Its derivative you can write as dy dx. Then you just solve this equation for dy dx. Divide both sides by 2y. Let's see here, get 3x squared plus 2x divided by 2y. That will be what dy dx equals. In terms of both x and y, ultimately this can be written in terms of x because you could replace y with a function of x. You could replace it by the h of x, which again in this particular case is easy to find. H of x would really be the negative square root of x cubed plus x squared. Now we want to find the slope at the given point, at this point right here. At that point, what is that slope? It'll be that derivative evaluated at that given point. You don't have to solve for y as a function of x, just plug the point into that expression right there. I'm evaluating that expression at the given point. In other words, replace x with 1 and replace y with negative square root of 2. And you'll get 3 plus 2 divided by 2 times negative square root of 2. And that can be simplified to negative 5 over 2 times square root of 2. If you like, you can rationalize the denominator, though I don't require that of my students in general. But if you do, by multiplying the top and the bottom by square root of 2, you'll get negative 5 over root 2, negative 5 times root 2 over 4. We can also approximate this with Mathematica to help us, or a calculator. It's about negative 1.76777. Okay, that's our answer. That is the slope. Now let's find it with parameterization. Just got to get this in text mode here. How do we do it with the parameterization? Well, I'm initially just going to tell you what the answer is, how to do it. I'm not going to explain it right now. I will explain it in later videos as I start talking about velocity and velocity vectors. But for this video, I will just show you what to do. We'll represent the slope as dy dx, but remember we've got a parameterization here now. We're thinking of x and y as depending on time to see the curve traced out as I showed you. You also can use the chain rule to derive this. I'm not going to explain it again right now. The way you do it is you find dy dt and divide by dx dt. I would encourage you to think about why that works on your own. Again, in this particular video, I'm not going to explain it. What is dy dt? That is g prime of t. That'll be 3t squared minus 1. What is dx dt? That'll be f prime of t. That'll just be 2t. We do need to plug in the particular point where we happen to be going through this point. What is the particular value of t, where we are at the point x equals 1, y equals negative root 2. So you need to set, for example, this equal to 1, t squared minus 1 equal to 1, and t cubed minus t equal to negative root 2, and find the value of t where it works. You actually can just solve one of those equations. T squared minus 1 will equal 1 when t is plus or minus root 2, and in fact you want to take the minus root 2 to get a minus root 2 when you plug it into g. g of negative root 2 is negative root 2. So we want to do this at the value of t, negative root 2. What will we get when we do that? dy dx will then be, when we use that value of t, plug it into here. We're plugging in minus root 2. 3 times minus root 2 squared is 3 times 2, minus 1, that'll be 5. On the bottom we will get 2 times negative root 2, just like before. This is going to be the same exact answer as before. We confirmed that we got the same thing. Let me also quickly add the tangent line to this plot very quickly. Within all this show, I'm going to put a plot. I will plot the tangent line. It's got a slope, again, of negative 5 square root of 2 over 4. That's the slope. You can type in the equation of the tangent line then like this. I would encourage you to think about why this works. This is an expression that will, as a function of x, we can plot it to get the graph of the tangent line. And let's make this be black. There it is. You can see it looks like a tangent line, and indeed that is the tangent line to the curve at that point. Here's your exercise. It's similar, except now we're parametrizing an ellipse. And here you can also solve for y explicitly as a function of x, but you don't have to. You can use implicit differentiation. I also want you to notice that with the parameterization, I'm using a different letter. I'm using a theta. It's a natural thing to do here. And here's the answer. Turns out the slope is square root of 3 over 9. If you do it with implicit differentiation, this is the method right here. If you do it with the parameterization, you get the exact same thing right here. I'm writing the dy dx equation in terms of theta like that. And here's an animation showing you what's going on here in this exercise that you should work on. That's the end of this video.